Alright, now I want to prove theorem 9.21, or 9.21, that if you have a function from an open subset of Rn to Rm, then here is a way to use the partials to talk about differentiability of the function. So this theorem is connecting partial and total differentiability, and it's going to do more than just what 9.17 did. Remember, we had theorem 9.17. It told us if we have total differentiability at a particular point, then we have all the partial derivatives at that point. But it didn't give us a converse. This theorem does give us a converse, but it comes at two costs. One cost is that it's not focused on a point, but on an entire open set. So it has to be done on an entire open set for this to work. And the second cost is that it's not just about differentiability, but it's about continuous differentiability. So it's not enough to just have the partials exist, they also have to be continuous. So you can think of this theorem as giving us a converse to theorem 9.17, but with these two costs associated with getting a converse. Open domain rather than just focusing on one point, and continuity of derivatives has to be brought onto the picture. Alright, so let's start by talking about the easy direction. 1 implies 2. Or let me assume the hypotheses first. So I just assume the hypotheses to make it clear that I'm making these suppositions and everything here. Then 1 implies 2. So assume f is continuously differentiable on its domain. Then that means f prime exists on all of E, and as a map from E to this space of linear maps, it's continuous, right? Now, we want to prove that these exist and they're continuous. Well, we already have that they exist, actually. By theorem 9.17, these partials are just fine. And they're defined on all of E, and they're these real-valued functions. And theorem 9.17 doesn't just tell us that partials exist, it tells us what they are in terms of the derivative. It tells us that, well, so let me write down the way we said it with theorem 9.17. We said if you take f prime x and evaluate it at ej, then that gives you a sum. It gives you a vector whose ith component is what I'm going to write down here, is djfi of x yeah, that's it. That's the component. So when you write this, this here is since what I've done is I've fed in ej, the jth standard basis vector, and then the numbers here are the number that shows up here is the ith component of the output. This is the ij component of the matrix that represents f prime x in the standard basis. In standard basis. So in other words, so let's say that is, theorem 9.17 is telling us that if you take pi ij of f prime x, that's what dj fi x is. In other words, so this is another way of stating theorem 9.17. Theorem 9.17 says that djfi, this partial, this is just pi ij composed with f prime. So, of course it's continuous, because it's this thing that we proved in the last video is continuous, composed with this thing that's continuous by assumption. We're assuming f is continuously differentiable, so that means this is continuous. So, which is continuous because it's a composition of continuous functions. Alright, so that's it for 1 implies 2. That was easy. 2 implies 1 is kind of hard. So we have now proven that if a function is continuously differentiable, then the partials exist and are continuous. But 2 implies 1 is hard. So let's think about what we would do for 2 implies 1. So for 2 implies 1, I get to assume that each djfi for all ij, each of these maps from E to R exists, first of all, so it is the partial derivatives exist, the limits that define these partials exist, and is continuous. Now I need to prove that f prime exists and is continuous. Of course, I can define, so we can define, I mean, how do you prove that f prime, how do you prove that f is differentiable? You have to have a guess for what the derivative is, and then prove that what you guessed as the derivative really is the derivative, that it fits in that limit definition of derivative. So we can define, here's a perfectly good guess, we can define g from E to L Rn Rm by saying, okay, well, let's just make it the unique linear map whose value at x, let's make it be the map whose value at x is the unique linear map that sends the jth basis vector to the column that we expect, namely this. So we could do this, right? This would define G, because it's saying for each x which linear map it is. For each x, it's telling us what it does to a basis, and knowing what a linear map does to a basis tells you what the linear map does to any vector. So this is a perfectly good definition of a function g. And if we make this definition, then by our work from the previous video, it's certainly true that g is continuous. So since when you make this definition, it has been rigged so that pi ij composed with g is djfi. And we have assumed up here that the djfi are continuous, right? We assumed that. So we have pi ij composed with f continuous for all not f, composed with g is continuous for all I and j. Therefore, by the work from our previous video, g is continuous. Remember, in the previous video we showed that if the pi ij composed with g are all continuous, then g is continuous. So far so good. We have proven in our work for 2 implies 1, we've proven that if the partials exist in our continuous, then we can define this linear map valued function to operate the way that we would expect if f were differentiable. And then whatever this, what we have defined then is certainly a continuous function. So it remains, and this is the hard part, it remains to show that G here is f prime. So it remains to show that G does what a map needs to do in order to be called f prime. So it meets the definition of the total derivative. And that's going to be the hard part. Okay, I think this is a good point to take a break if you want to, and I'll just put the next part in the next video. And I'll make it depend on this video.